Welcome to One-on-One, a show dedicated to business and the entrepreneurs and leaders that start, run, and own the innovative and interesting companies in our area. I'm your host, Alex Ruggieri. My guest today is David Carroll of CU Aerospace. Dr. David Carroll is the president and co-founder of a CU Aerospace company located in Champaign-Urbana, Illinois. CU Aerospace operates principally as a government contractor working in space propulsion, nanosat fabrication, high-energy lasers, self-healing composite materials, astrodynamics, and other advanced aerospace technologies. David received his degrees in aeronautical and astronomical engineering from the University of Illinois at Urbana-Champaign with a BS in 1985, an MS in 1986, and a PhD in 1982. Dr. Carroll serves as the chair for the Plasma Dynamics and Lasers Technical Committee of the American Institute of the Aeronautics and Astronomics, and he was inducted as a fellow of the AIAA in 2011. Stay with us. We'll be right back to talk with Dr. David Carroll. We're back. My guest today, Dr. David Carroll from CU Aerospace. Welcome.
Thank you. Good to be here.
CU Aerospace. Who would have thought? Incredible. We have an aerospace company right here in Champaign-Urbana, and I'm so excited about your technology and about the things you're doing, and I want to shine a light on that and talk all about it. But before we do, let's learn a little bit about you. Can you tell us where you're from and how you came to Champaign-Urbana?
Okay. Well, I was born in Princeton, New Jersey.
Okay.
My parents came here when I was a year old.
All right.
And my father is a professor of mathematics, now emeritus. My mother is a professor of history and political science. She's went over to Purdue some years ago. But anyway, they came here when I was a year old, and I've mostly been here since, with the exception of a couple of years in LA.
Okay. So there's no question, really, was there, that you were going to college when you were growing up in that household, right?
It's probably a fair assessment.
Fantastic. Well, tell us about CU Aerospace.
Okay. So CU Aerospace spun out of the university in 1998.
Okay.
We had some ideas of what things we could maybe commercialize from an aerospace technology standpoint. And we got together 6 co-founders and decided to take a shot at it.
Mm-hmm.
And
this was what year?
That was 1998.
Okay.
1999 we started getting actual contracts. So the first year was a bust, and let that be a lesson to entrepreneurs that you got to kind of stick with it.
Yeah.
And so now we are in our 14th year of operation.
Fantastic.
And slowly growing.
Great.
Slowly growing.
Tell us about the early days. What was the technology that you wanted to commercialize?
So the early contracts were related to what's called electric propulsion, where you take a gas or some propellant and you use an electric discharge to energize that flow. And in that time period in 1998, we were working with what's called a pulsed plasma thruster, where you take Teflon as your propellant, which is great because it's not explosive at all, and then you put a 3,000 volt discharge arc across that. You ablate a little bit of the Teflon and these pulses, and turned out that that was a very precise thruster system. We got close to flying it, but the contract we were hoping to get, or the program, got canceled before we got on contract. So
okay.
Didn't quite make it with that one, but now we're working on another propulsion system for which we just got some very good news to build a prototype flight system for small CubeSats, which are 4-inch by 4-inch by 12-inch small nanosatellites. And those are pretty exciting little things. You know, 10 years ago they were pretty much, yeah, what can you do with them? But now if you think about what's built into your iPhone, you can start to get a sense for what kind of power you can put onto a satellite.
Wow.
A small satellite.
And what would you use the small satellites for?
You can use them for a number of things. The universities are, of course, interested in them because research. The university has a CubeSat class, which I'm actually co-teaching next semester. And you can use these for scientific experiments. You put them in low Earth orbit, and they can get information on atmospheric phenomenon or particles, the magnetosphere of the Earth, things like that. And then there's sort of obvious Department of Defense applications where you could actually spy on people.
Wow, wow. Now, are these also using Teflon as a propellant?
No, so the new system is using what's called a microcavity discharge on a gas propellant. And so you've got a gas going through a small rocket nozzle that's about diameter on the order of 1/4 of a millimeter. So very tiny.
Wow.
And then the discharge that you put on that gives you additional energy in your flow, so you increase the thrust that way.
And so this technology increases the thrust of the gas, but it also gives you a great amount of control, as I understand it.
Right. So
which is really important when you're trying to manipulate a satellite.
Yeah, we've teamed with a company in California called VACO Industries, and the combination of the two, the marriage of the two technologies of their system and our system, looks like it's going to be a wonderful little thing for small satellites.
Fantastic. And how do they get up into the atmosphere? I mean, into the low Earth orbit or wherever they're going?
So you have to have launch vehicles. There's different alternatives. Some launch vehicles, you could put 18 CubeSats on a single launch vehicle and pop them out, get them into low Earth orbit and pop them out at different points in the orbit. Other options are these things come in small pods that eject them with a spring, and so you can actually piggyback on larger payloads. And then another option is like Orbital Sciences has something called the Pegasus launcher, which launches from underneath the wing of a large plane. And these are small enough satellites that you could launch those.
And then does that actually use rocket propulsion, comes out from under the wing and then goes into the
exactly
low orbit that way?
Right.
Wow, incredible, incredible. So now you have some other technologies too. I know you're doing some solar sails.
Solar sails.
Let's talk a little bit about that.
Okay, so solar sails. With solar sails, what you're using are large, very thin blades of material, usually like an aluminized mylar or something like that. And you're using the solar photons as your propellant. So the photons come in, they reflect off of the material, and they impart momentum. Now, a photon by itself doesn't have much momentum, but when you think about the number of photons that are being emitted by the sun and the number that can hit a large sail, then you can actually start to get significant thrust from that kind of technology.
I want to talk more about this because that's almost counterintuitive, because we put our get our suntan and the photons hit us and give us a little suntan. We don't ever think of it in terms of creating thrust. But I'd like to explore that a little bit when we come back. We've got to take a short break. And when we come back, maybe you can tell us how that really works.
Okay.
Fantastic. Stay with us. We'll be right back after the break. We're back. I'm your host, Alex Ruggieri, and today we're having a great discussion about CU Aerospace, maybe a company that you didn't know existed right here in Champaign, with Dr. David Carroll. I'm so excited about this company because you're doing, it's like the little company that could, you're doing all these really wonderful things. And we talked a little bit about your CubeSat technology, and we were just before the break talking about the solar sail.
Right.
And this idea that you can get up there in outer space, for lack of a better description, or space, and this array would open up, and then propulsion is created merely from photons. Can you tell us
From photons.
how that works?
Yeah, so the photons hit the solar sail material, impart momentum onto...
Some energy is transferred.
Some energy is transferred, and you can change the orbit of your satellite. So if you make the blades long enough, we have a concept that one of the co-founders, Rod Burton, came up with called ultrasail, that if you make the blades long enough, like 5 kilometers long.
Wow.
Yeah.
That's long.
Okay, so then you have 4 blades, so a big cross. You can get enough momentum imparted so that you can do scientific missions, say, to Jupiter or Saturn in the same kind of time frame as chemical propulsion.
See, this is really important because what little I know about this technology, I know that it's very expensive and there's a lot of weight involved with chemical propulsion systems.
Exactly.
And so there's a real advantage to your system.
Right. So with a standard chemical system, you have what's called a payload fraction of only about 10%, meaning your science payload is 10% of the mass that you have put into orbit and then launch to or send it to Jupiter. With the ultrasail concept, the payload fraction is 50 to 60%. So now you can either have much larger payloads going to Jupiter or Saturn, or you could go the other way and have much less massive payloads which are cheaper to launch. And that's probably the way NASA would opt to go with.
And your technology using the solar sail, will it get there to Jupiter within the same time frame, or is it within tolerable limits? Or
yeah, so we would be in the same time frame as long as you're making the blades 5 kilometers long or something like that.
Yeah, which is no big deal in outer space.
Yeah, well, that's the neat thing is you can have these tip satellite type things and envision a big roll of aluminized saran wrap. That's a little crude in the description, and then these tip satellites actually just have little thruster systems and pull it out. And then it gets really elaborate because you can then, those tip satellites can twist the blades and counter-twisted directions, if that's a word. And then you get like a windmill effect because the photons will start to spin the whole thing up, and you get a centrifugal stabilization to help the satellite.
Wow. Wow, that's just incredible. And you probably use your little mini thrusters as part of the array.
Exactly, you could do that. And NASA funded us to do a risk reduction experiment where we built a pair of small CubeSats that will deploy 250 meters of solar sail film between them, and that's to be launched in low Earth orbit. The hardware is now completed, which is great. We just finished that in September, and now we're looking for launch funds.
Wow. Well, where are your materials manufactured?
A lot of the stuff is manufactured at the university.
Really?
We work very closely with the university. It's been a wonderful relationship, working with them on a variety of programs. And so we can, we have lease agreements for lab time and facility use agreements. And then we also can utilize university shops to help out. You know, we pay the university.
Wow, so you're doing the manufacturing here, and from what I hear you say.
We do a lot of it here. Some things will require manufacturing elsewhere, like the thruster systems that we talked about. The bulk of those will be built at this other company, Vaco Industries.
That you're partnering with.
Right.
Now, this is so exciting. I have to ask, now the solar sail, you've got the contract, NASA's funding it. Is it going to go into outer space? And if so, when?
Well, we're trying to get funds. We applied for a launch initiative for CubeSats, or the university did just a few months ago. and we're targeting a launch date sometime in late 2013.
Wow.
Yeah.
And how exciting. And so once it goes up, it's purely research at this point, right? I mean, it's not going anywhere. It's not going to Jupiter.
No, this would be a risk reduction experiment.
Okay.
What you're trying to do is demonstrate that the solar sail film, as planned, could actually
Will perform
and raise the orbit.
Mm-hmm.
And then we'll have to twist a different direction and use aerodynamic drag to pull us down and burn up.
Wow. So you really are in low Earth orbit then?
Yeah, we're shooting for about 750 kilometers or higher.
Mm-hmm.
And that's about twice the altitude of the space station.
Oh, wow. Okay.
So it's still up there, but it's surprising how much atmosphere is still there.
There's still atmosphere that far.
Yeah, even the space station has little control thrusters on it, and they have to reboost the station periodically.
To prevent drag from pulling it down.
Right.
Wow. How fascinating. This is incredible stuff, and I'm just so glad that we've got a little company here in Champaign-Urbana is participating in such a big way in the future. Believe it or not, it's time for our second break here, so we'll take a break for our sponsor's sake. And speaking of the future, when we come back, maybe we can talk about that.
Okay.
We were talking about this wonderful project which you're working on, the solar sail, which you've been given a grant by NASA for this risk reduction experiment, and the sail you hope to have launched sometime in maybe 2013.
Yeah, probably late 2013.
Late 2013, which is just an incredible project, and I'm so excited about it. I'd like to talk to you about what you think the future holds for aerospace, for CU Aerospace, and hopefully you're going to stay in Champaign-Urbana and the future for Champaign-Urbana in your company. But I know you have other technologies too. You have some laser technology, and how does that work?
So we've been involved in what are called high-energy lasers for a long time. These are the type of laser you think of for Department of Defense and
weapons grade.
Weapons grade, shooting down missiles at long range.
Yes.
Now we only work with subscale stuff, so we don't actually shoot down missiles ourselves.
Right.
But what we are working on is next generation versions that would be potentially more efficient and better overall systems for the military. So one of the items that we work on is called an electric oxygen iodine laser, where you electrically discharge a gas flow of oxygen and excite the oxygen molecules. They transfer their energy to the iodine, you laze on the iodine, and this version of the technology is similar to what was called the chemical oxygen iodine laser, or COIL, which was on the airborne laser program, which had successful demonstrations in 2010.
But it's a really big...
That's a big honking aircraft. Yeah, so it's megawatt class. So think about your light bulb at 100 watts, and now multiply that by 10,000. Wow. And then put it in a beam the size of your fist. And you can project that a pretty good distance.
You could probably burn holes on the moon with that. I don't know.
I haven't thought about that.
Well, what's different about your technology than the COIL?
Okay, so the COIL uses chemicals, and some of them heavy. It requires a reaction between a liquid bath of hydrogen peroxide mixed with potassium hydroxide.
Whoa. Sounds caustic to me.
Yeah, and that's in like 50% concentrations or so. So
very high concentrations.
Yeah, the hydrogen peroxide is not the 3% stuff that you buy in the grocery store.
Right.
And that's fairly unstable at even 0 Celsius. So you have to chill it to -15 or -20. Okay. And then on top of that, you mix in chlorine gas to get your excited state of oxygen. And it's a very efficient process at that, but from a logistics standpoint, it's a little...
you have to have all that on the airplane flying through the atmosphere.
So you put this on 747 and you start while it works, one starts to be concerned from a logistics standpoint. So the electric version, we believe we can deliver just as much power for half the weight. And we don't have this basic hydrogen peroxide, and we don't have chlorine gas.
Wow.
So
That's huge.
It's just electric discharge.
Reduce the weight by 50%, reduce the caustic issues with all of the chemistry, and produce the same wattage or megawattage or whatever you call it.
Right.
That's incredible. That's incredible.
Right.
You folks are the future. This is incredible technology.
Yeah, one of the hard things in aerospace that you have to realize is that everybody is very concerned with safety, justifiably so. And so the technologies take a long time to mature.
Because you want to do it right.
You want to do it right, and you don't want people dying because of it.
Well, I'd rather have your technology up in the atmosphere than a big old airplane full of caustic chemicals that somebody's going to try to shoot down.
Well, they could try and shoot you down either way. But
yeah, that's true. That's true. But at least you're not going to have hydrogen peroxide bath dump on your town.
You will be faster.
Yeah.
You will be a little bit more nimble.
Yeah, a lot less weight. Well, we have just a few minutes left. What do you see as the future for CU Aerospace?
So we will continue exploring the high-energy lasers. The CubeSats and solar sails and small propulsion systems are all a big factor for us. And probably our first super serious product will be the small propulsion systems. And then we are also involved with self-healing composite materials, which you take 50-micron capsules of a healing agent, like a glue, you embed that into a resin of a composite. And then if you think of composites like a tennis racket or a golf club, you get these little fractures that turn into big fractures. The self-healing composites will seal those small fractures as they come. Wow. And then various software applications we're looking at as well.
Sounds like a bright future for CU Aerospace.
We hope.
Well, we wish you all the luck in the world, because we know you're employing people right here, and you've got an office right downtown, and we wish you all the success in the world.
Well, thank you very much. Our success to date would not have been possible without the university.
We're lucky to have them. We really are.
Yep.
And good people like you. Thanks so much for being on the show today.
Thank you.